Okay, AP Chemistry, this is your day 64 assignment, the day right after Thanksgiving break. It's on hybridization, and it's a fairly long assignment in terms of number of questions, so I'm not asking that you answer everything in complete sentences. The first 6 questions I would like you to answer in complete sentences, and it might even take a little more space than I gave you here, so I'm going to do it on line paper to write out a thorough answer for you. Okay, so the first question is, what is the difference between Sp orbitals and sigma and pi bonds? Okay, so number 1. So S and p orbitals. What they are is they are the orbitals that belong to a specific atom. And every atom has an s orbital. Only atoms from the second row down, second period down, have p orbitals. So they belong to individual atoms. So S and p orbitals belong to individual atoms. From the second row down. Okay. Sigma and pi bonds are different. They are bonds, they are molecular bonds that stretch across from one atom to another, that allow an atom to bond into a molecule, into a covalently bonded molecule. So sigma and pi bonds connect atoms covalently. Those are the ones that share electrons. To form molecules. Let's say that again. S and p orbitals belong to individual atoms from the second row period down. Sigma and pi bonds connect atoms covalently to form molecules. All right, so that's the answer to number 1. What is a sigma bond? 2. A sigma bond it's a bond between two atoms that lies on the axis directly between the nuclei of those atoms. So I'll just draw a little sketch here in just a second. And that axis is called the internuclear axis. So if this is a nucleus and this is a nucleus, and you draw a line between them, it's any bond that lies on this line directly between the two nuclei. As compared to what? Well, we're going to see in a minute, but is it compared to a bond that lies down below the two nuclei or up above the two nuclei? But if it lies right on that axis, that's called a sigma bond. Okay, sigma bonds are either s orbitals, such as hydrogen. All hydrogen has is an s orbital, or sp, sp2, or sp3 hybrid bonds. Okay? All right, and you're going to see examples of these. So what seems like kind of just a formal definition will make more sense as you see examples. Okay, what types of orbitals form sigma bonds? Well, I just answered that. So this is going to be 2 and 3. The answer to that is this. That's the answer to number 3 right there. Okay, sigma bonds are either s orbitals or they're sp, sp2, or sp3 hybrid bonds. All right. Okay, what is a pi bond? So number 4. A pi bond is a bond So a pi bond is a bond that's formed by unhybridized p orbitals. In other words, orbitals that just stayed just the way they were in the original atom, and they didn't hybridize into sp, sp2, or sp3 orbitals. What types of orbitals form pi bonds? And I answered that one right there as well. So that's the answer to 4 and 5. It's unhybridized p orbitals form pi bonds. Okay, only unhybridized p orbitals form pi bonds. Let's see, what else? I want to add one more fact about pi bonds. Pi bonds do not lie on the internuclear axis, or on an internuclear axis, because there can be several in some molecules. There can be many, in fact. In other words, they're not right in between the two nuclei of the atoms. Okay, they're either above or below. And again, this will all make more sense when you see some examples coming up here very shortly. All right. Number 6, sketch an sp orbital. So 6, sketch of an sp orbital. Camera up here, sorry. And this is the same shape for an sp, an sp2, or sp3. sp2 and sp3 are a little bit bigger because they stretch out a little bit farther. They include more orbitals. It is going to simply look like this. It's the bowling pin. And if I were to actually draw it, it should be paired up with at least one other sp orbital. So I'll just draw them all. This is sp. If you have a trigonal planar molecule, and actually I should draw the knob, what I call the knob there, another one there, and another one there. They kind of stick out behind. This is sp2. And then if it's a tetrahedral, you have a knob there. You have it going off in a tetrahedral direction like this. You have another knob. You have it going off to the back side. That one's going out the back. And then another knob, and this one's coming out the front. So 1, 2, 3, it's tetrahedral. You have to use your imagination with my drawing here. And that's an sp3. Notice sp is S and P. That's 2 letters. That means there's 2 different bonds. sp2 is trigonal planar, so that's SPP, so there's 3 lobes. And sp3 means SPPP, that's 4, 1, 2, 3, 4. All right? Okay, next. Sketch a pi bond that is parallel to this page. Okay, so for number 7, to sketch a pi bond, it's going to look like this. If this were the nucleus, remember we said pi bonds up above are not on the internuclear axis. That is the internuclear axis right there, this line between these 2 nuclei of 2 different atoms. But a pi bond looks like this. If it's parallel to this page, it's going to look like this. What it is, and I'm going to draw this as kind of a dashed line, it's 2 p orbitals. There's a p orbital from one atom, and there's a p orbital from another atom. And what they do is they kind of stretch out and they encompass each other, and they form a bond up above. And I should actually draw kind of a bottom to it like that, because there's an open area there. So they're really this area here, but it's also the same pi bond as one that goes down below. And it's this area here. So it's the shaded, the dark shaded area. That's the pi bond. It's the same pi bond. On top and on bottom, that's the same pi bond. It looks like 2 different bonds. It's just the same bond, but it has 2 different locations to it. just like this is the same bond, but it has two different lobes to it. So that's a pi bond. It's not on this internuclear axis. Okay, so that takes care of number 7. Now number 8. I'm asking you to sketch an sp orbital below. So an sp orbital takes up an s and one of the p's. That's why it's called sp. And since it's half p and half s, it's going to form halfway in between these two orbitals. So it's going to be right here, like this, and there's sp, and this is an equal sp. They're both the same. Then these two are unhybridized. That's what we were talking about earlier that form pi bonds. It's unhybridized p orbitals, and they stay exactly as they are before. So they stay at the same level. If I just draw a dashed line, they stay at the same level. There's py, and there's pz. Okay, so that's an sp orbital right there. That's how you would draw the sp orbital. There's two of them. Okay, how about Sp2 orbital? So this is going to be, it's going to encompass an s and two of the p orbitals. That's why it's Sp2. And since 2/3 of it is p, it's going to be 2/3 of the way up to the p orbitals. So I'm going to draw it like this. And there's one of them. And there's a second one. And there's a third one. So it was formed from 1, 2, 3 different orbitals, and it forms 1, 2, 3 orbitals. Okay, you don't gain or lose any the number of orbitals. And then the unhybridized is this pz, so that stays at exactly the same level as this pz, and that's an unhybridized orbital. Now, since double bonds and triple bonds are, well, let's talk about that later. Okay, next is an sp3. And this one is going to take up all of the p orbitals right there. And it's going to be 3/4 of the way, since 3/4 of it is p. Let me get on screen here. Since 3/4 of it is p, then it's going to be 3/4 of the way up from the s to the p. So I'm going to draw it way up here. And it's going to be sp3, sp3. So they're all equal energy levels. And this, by the way, would be tetrahedral. This would be trigonal planar. Look on your sheet, on the chart sheet that you've been given. Planar spelled P-L-A-N-A-R, something I learned over the break. And this one is going to be linear. Okay. All right, so that's how you would draw these orbitals using the Aufbau levels. Okay. All right. Now we're going to go on and we're going to do about 8. Yes, 8, and that's why you don't have to write complete sentences for all of these answers. It's a long assignment in that sense, but once you get the hang of this, you're going to whip right through these. Okay, they'll be really easy. Okay. Okay. What we're going to do is we're going to answer a series of questions for a number of molecules. Now, the first 4 or 5 of these are from a video that is on YouTube that I've gone ahead and posted a link to in the Day 64 module. It is an excellent video. It's as good a video as I've seen on this, and it's pretty short. It's only 12 minutes long. I'll talk to you more about that, but I would recommend you watch that video before doing this. And I would recommend that you watch it once every night this week. It's only 12 minutes. And by Friday, when you have your test will be on Friday on this. This will be firmly ingrained in your brain. But again, you need to do exercises and need to practice this some. Okay, so we're going to go ahead and answer these questions for CH4. It's one that we've talked about many times in class. And then we're going to try to sketch it. When I say try, I mean I'm going to try to sketch it. It's not my strong point. But we're going to sketch the sigma and pi bonds for a CH4 molecule. So first question is, what is the domain geometry? So you simply find that by going to this sheet. The domain geometry right there is tetrahedral if CH4. Okay. So here's what the first thing you do is. You look at how many electron domains does it have. It has 1, 2, 3, 4. So you come down here. It's tetrahedral. And you can see that it is an AX Sp2 it has no lone pairs, so that makes it tetrahedral. Okay. What is the molecular geometry? So whenever you have no lone pairs, the domain geometry and the molecular geometry, in other words, the actual shape of the molecule, are the same because you have atoms attached to all four of those locations. So Ax4E0 is also tetra. So these are things we've done before. We did this before the break, these types of exercises. What is the angle between the bonds? You might as well learn these. I'm not really requiring that you memorize bond angles, but this is a pretty common one that you'll come across a lot. It's 109.5 for a tetrahedral. Again, notice I'm not writing complete sentence answers, and neither do you have to do that. Okay, just answer the questions because I want you to run through a lot of these molecules. How many electron domains surround the carbon atom? Well, really, I should have asked that question first before we asked this. So maybe on the future questions, I'll answer D before I answer the other three above it. Okay, there's 4 electron domains. 1, 2, 3, 4. An electron domain is simply any place where there's a lone pair or bonding electrons. So remember, these single lines could be drawn as 2 dots. You don't do both. You don't draw the line and 2 dots, but I'm just showing you that it's represented by this. And so there's 4 electron domains. Electron domains can either be bonding areas or lone pairs. In this case, there are no lone pairs, so it's these bonding. So how many electron domains? There's 4. And that's all you need to do is write the number. Now, here's a term I haven't introduced you to yet, and you might come across it in some books. Steric number is the same as electron domains. So these could be called steric regions as well as electron domains, but steric number is the same thing. So there are 4 of those. There are 4. The steric number for the carbon atom is 4. There's 4 electron domains. It's just a different name for it. It's exactly the same thing, just a different name. What is the Axc notation? Well, I needed that to do the first part, so it was Ax4. So maybe I'll do these in a little different order. It's one of the reasons maybe you want to watch the video and see how I do these first. What is the hybridization of carbon? So the hybridization of carbon, you come over here and you see that it's tetrahedral. So it's an Sp3. It has to have 4 different bonding hybrids. Okay, so it's Sp3. Anytime you have Ax4E0 or Ax anything that's a tetrahedral domain geometry, it's going to be Sp3. What's the hybridization of hydrogen? It's not a trick question, it's just to be sure you understand the concept. Hydrogen cannot hybridize. You must have a p orbital. An atom must have a p orbital in order to hybridize. So hydrogen does not hybridize. It simply bonds with the only shell that it has, the only orbital it has, which is the 1s. So you can just simply put none, and then you might want to write an explanation here to be sure you understand why. Hydrogen does not have a p orbital. You need an S and a P to hybridize. That's what hybridization is. It's mixing the two. Okay, identify the sigma bonds, which I kind of blew it because I came over here and wrote where I was supposed to draw, sketch the sigma and pi bonds. So basically, it's what I drew on the previous page. So it's a knob and a bowling pin, upside down bowling pin like that. And then there's one going down here, kind of away from you, or kind of towards you actually. Another one going kind of down here away from you. And then another one coming kind of out towards you again. Again, these are all 109 degrees, 0.5 degrees. And that's what it looks like. It's tetrahedral. Anyway, use your imagination. It's going to look like that. All right? Okay, identify the sigma bonds. Okay, so these are all sigma bonds. Identify the pi bonds. There are no pi bonds because there are no unhybridized p orbitals. Everything is an sp in this tetrahedron. So there are no because all p orbitals have been hybridized. And p and pi bonds require unhybridized p orbitals. Okay, all right, so that takes care of the first one. So as you get good at this, we're going to move through these a little faster, and I'm going to show you probably the preferred order of answering these questions rather than the order that they're given. Okay, so next up is C2H4, and there's a diagram. I'm not going to make you do the Lewis dot, but you should know how to do the Lewis dot of C2H4. We'll practice that separately. I want you to focus on hybridization now. So what is the domain geometry, molecular geometry, the angle between, how many electron domains surround the carbon? So let's start with that one. So there's an electron domain is anywhere where there's a bond between an atom. So we're going to start with this carbon and just focus on this carbon because the answer for this carbon would be exactly the same. So this carbon has 1, 2, 3 electron domains, places where it's either bonding with another atom or it's a lone pair. Well, this carbon doesn't have any lone pairs, and yes, it does have a double bond, but that's considered to be one electron domain. It's a place where there are electrons, in other words. That's what the word domain means, a place where there's electrons. So the answer to D is there's 3 electron domains. And what's the steric number? It's 3. It's always the same. Those two are always the same. I'm just trying to introduce you to this new concept. What is the Axc? So it's the best to start with D, E, and F, and Axc for this is going to be A. It has 3 bonding domains, 1, 2, 3, where there's bonds. And it has no lone pairs, so it's E0. Okay. So now that we've got that, let's go back to A and answer A. So what is the domain geometry? Well, we just come over to our sheet. It's Ax3E0. That's trigonal planar. And since it doesn't have any lone pairs, it's not missing any of the atoms. Its molecular geometry is trigonal planar. So we're going to answer trigonal planar. And the molecular geometry is the same because it's an E0. Okay, what's the angle between bonds? Again, you can come over here, but it's basically a triangle. So its triangle has 120 degrees between angles. Okay, what's the hybridization of the carbon? Okay, so again, it's trig planar. You just come back here and you look right there. There it is, Sp2. Okay, it has to form 3 bonds. I'm just going to write this out just to really emphasize it. S, P, P. There's 3 letters there, so it's 3 different bonds that were formed. This forms 3 different bonds. What's the hybridization of hydrogen? Same thing as I answered in the last question, none. It doesn't have a p orbital, it just has its little 1s orbital to bond with, and that's what it bonds with. There's no hybridization there. Okay, identify the sigma bonds. Okay, so there's 3 sigma bonds. Sp2 means there's 3 bonds. They're going to look like this. And why don't we sketch them over here? There's going to be one, if I take this carbon as my example, there's going to be one sticking out that way. And then there's the hydrogen right there. I'll just write an H there. There's another one. Remember, it's a little bowling pin. Sticks out like that. And then there's a hydrogen right there. And then there's one going this way, like that, that's bonding with this other carbon over here. And it's got its little bowling pin. So this is an Sp2. This is an Sp2. And this is an Sp2. And there we go. So the sigma bonds are these 3 right here. Okay, there I can just draw an arrow to that. Okay, now let's draw the other carbon. It's going to look exactly the same except it's pointing in the other direction. So I've got my bowling pin here that's going to come over, and there's a sigma bond, Sp2. It's also going to have Sp2. Notice this is the internuclear axis between the 2 carbons. By the way, I should have pointed out here, this is the internuclear axis between the carbon and this hydrogen. And this is, if I draw a straight line between this carbon and this hydrogen, this sp2 orbital and hydrogen's 1s orbital, they both lie on that line. Okay. So now I'm going to do the same thing I did here. I'm going to draw my bowling pin going out there like that, and it bonds with a hydrogen out here. And I'm going to draw my other bowling pin coming down here, and it's going to bond with a hydrogen down there. Again, these are sigma bonds. Sigma, 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 because they lie directly between the nucleus of two different atoms. So these are all the sigma bonds here. You got 1, 2, 3 on this atom, and you've got 1, 2, 3 on this atom, right there, on this carbon atom. Now, identify the pi bonds. This is what double bonds are. Double bonds are formed by unhybridized p orbitals. Remember we said that which form, this is very important, which form pi bonds. And remember we said that pi bonds do not lie on an internuclear axis, so where do they lie? Well, the unhybridized orbital, I'm going to draw it as a dashed line. The unhybridized p orbital, and we can call this the py orbital, it doesn't matter which one you call it. It goes like that. It looks just like it looked before these two atoms got together. And this carbon atom also has an unhybridized. So 2 of the 3 p orbitals for this carbon became joined in with the s to form the sp2. So you have an s and you have a p and a p. That's the px and the py, or pz. It doesn't really matter. It's just as long as you're consistent. I usually, up and down, I usually think of as the y-axis. So there you have 2 p orbitals that are unhybridized, but they're each holding an electron. And so what they do is they form the pi bond. Notice it's not on the internuclear axis here between the two carbons. It's up above, and it's also down here, down below. So this is a pi bond right here, and this is a pi bond. It's the same pi bond, okay? These two are the same pi bond. They happen to be in 2 different locations, but they're the same pi bond. So these are the pi bonds right here. One there, and the same one, just in a different location, is right there. Okay? And so those are your pi bonds. They're not on the axis between the two nuclei. All right, let's keep going. Next one is number 11. And as I said, we're going to start down with D. How many electron domains surround the carbon? So let's just pick one of the carbons because they're identical. They're just mirror images of each other. So if we took this carbon, it has 1 electron domain there and 1 electron domain there. So the answer is 2. What is the steric number of the carbon atom? It's 2. Again, we're just talking about this one, but the same answers apply to this one. What is the Axc notation for C2? So for one of the carbons, it's going to be Ax2 because it has 2 bonding domains, and it has no lone pairs, so it's E0, Ax2E0. Now I'm going to go up and give the domain geometry, so you simply come over here, and it's Ax2E0, so that's going to be linear, and the molecular geometry is going to be linear. So it's going to be linear and linear. What's the angle between them? It's 180 degrees. Okay, right there is 180 degrees. Again, you just get that off your sheet right there, 180 degrees. It's a straight, it's a linear molecule, straight line. What is the angle? 180. Okay, what is the hybridization of each carbon atom? So the hybridization here is, you just come over here to your chart, and it's sp. That's going to form 2 bonds. Sp forms 2 bonds. So it's sp. What is the hybridization of the hydrogen? Same thing as we've said before. There is none. It cannot hybridize. identify the sigma bonds. So here's where it gets a little interesting. You have a carbon, and it's going to form this bowling pin coming out here like this. That is an sp orbital. It's going to form another bowling pin on the back side. That is an sp orbital. What's that back side going to bond with? It's going to bond with this hydrogen out here. That's a single bond. Now here's the other carbon over here, and it's going to have a bowling pin, an sp, coming out here. These two are going to have the same configuration except backwards, mirror image, sp. And then this carbon is also going to have another bowling pin coming out this way, and that's going to bond with that hydrogen on the other side. So there you go. There's your sigma bonds right there. So sigma bond is right there because it's in between the carbon and the hydrogen on a straight line. There's another sigma bond right here because it's in between the two carbons on a straight line. And there's another one right here because it's in between this carbon and this hydrogen. Those are the sigma bonds. Now what about the pi bonds? That's where it becomes interesting. And this is where my art skills are going to let me down a little bit. You have one that's parallel, that's actually lying on the plane of the page here. So I'm going to draw a p orbital like this. It's unhybridized. And a p orbital like this. Again, if you're questioning the unhybridized part, go back to this sheet, and we see that sp, that's not what I wanted to show you. Well, anyway, it's unhybridized up and down. It's on the plane of the page. So does this one. So this one also has a p orbital that's up and down. It's directly lying flat on the page like this, and that's a p orbital. So they're going to form a pi bond. They're going to stretch over like this, and they're going to form a bond. Each one has an electron, and that forms a pi bond. And this is the same pi bond. Okay, don't think that these are two different bonds. So that is one of the double bonds. Pi bonds, unhybridized p orbitals form pi bonds, and that's where double bonds come from. But you have yet another one, and you're going to just have to use your imagination on this one. Imagine that you have these p orbitals coming out of the page towards you, like this, and going back into the page away from you. I'm not even going to try to draw that. This one is coming out of the page toward you and back directly into the page away from you. So up here there's going to be a p orbital. I have my pen about half an inch above the page. There's a p orbital up here, and if I could go down underneath the page a half an inch, there would be a p orbital back there. So you have two unhybridized sets of p orbitals, the py and the pz, or whichever p you want to call it, xyz, it doesn't matter. You have two sets of them, and those form the double and triple bond. So one of the p orbitals forms the double bond, the other one forms the triple bond. Doesn't matter which you say is which, okay? So there is the pi bond right there, and the same one is up there. And then you have another one up above the page here, and another one down inside the page, down below the page there. And those would be the two pi bonds that would form the double and the triple bond. So single bonds are formed by sigma bonds. So there's sigma, there's sigma, there's sigma. They're directly on the axis between all of these atoms. And then the pi bonds form the double and triple bond. Okay? Alright, when you watch the video that I recommended, the perspective is the graphics are good. They're really good, and they'll give you a better sense of what I'm talking about here. Okay? Alright, we are going to keep going. And now we're at ammonia, Nh3. So again, I'm going to start at D. How many electron domains? So remember, electron domains can either be bonding or non-bonding. That is to say, lone pair electrons. So there's 1, 2, 3, 4. So there's 4 electron domains. That's 4 steric regions, exact same thing. The Axc notation is A. There's 3 bonding domains, 1, 2, 3, AX3, and there's 1 lone pair, E1. Okay, so there you go. So what's the domain geometry? Just come back to your sheet, and there it is. It's AX3E1. It's tetrahedral is the domain geometry. And the molecular geometry, though, since it's missing that one atom on top, it has that lone pair, it's going to be trigonal pyramidal. Okay, it's going to form like this shows right here, kind of a pyramid, a three-sided pyramid. These lone pairs push down the bond angles on these bonded atoms right there. So that's going to be trigonal pyramidal. Okay, the angle is, it's less than 109.5. If for this it's 109.5 and the lone pair pushes these guys down here, then it's going to be less than 109.5. That's all you can say. You can't say exactly what it's going to be, but we're just going to say less than 109.5. All right, what is the hybridization of nitrogen? We've done this for the umpteenth time here. None. Okay. Oh, whoops, wrong. It's none for hydrogen, so let me go ahead and write that since I just said it. For hydrogen, it's none. But what about for nitrogen? Okay, well, it's got 1, 2, 3, 4 electron domains. That means it's going to be an Sp3. Again, that's all you have to do. Tetrahedral domain geometry is always going to be Sp3. Okay, so it's going to be Sp3. So you come over here, and again, I try to draw this the best I can. So here's tetrahedral here. It's trigonal planar. Here's one going back into the page. Back into the page. And here's another one coming out again this way. And these are all kind of pointing downward. So this is Sp3, Sp3, Sp3. And then the fourth one is going up. And that's Sp3. Now these all have hydrogens bonded to them. This has a hydrogen, this has a hydrogen. You can pick any three you wanted to say the hydrogens are bonded. It doesn't have to be the three on the bottom. That's a hydrogen. So these are sigma bonds right here because it's directly between the nucleus of the nitrogen and the nucleus of the hydrogen. Same with this. Directly a straight line between the nucleus of the nitrogen and the nucleus of the hydrogen, and the same thing there. Okay? Now what is this Sp3 doing? It's got these lone pairs, so I'll just draw a couple dots up on top. That's where the lone pair is. And it's pushing this bond angle down so it's less than 109. So you have 3 sigma bonds. Since you don't have any double or triple bonds, that's your signal that you have no pi bonds. Pi bonds are always double or triple bonds. That's how double or triple bonds are formed. So that's basically it. So the sigma bonds are these guys. And identify the pi bonds. There are none. There are no pi bonds in this. If there's no double or triple bonds, there's no pi bonds. All right. So hopefully this is kind of making some sense. And we're going to keep speeding along here. Okay, so next one is water. Okay, so water. How many electron domains? So 1, 2 for the oxygen we're talking about. How many electron domains surround the carbon? I didn't change that. Shoot. I'm going to change that to oxygen. I'll be sure before I print these I change them on your copy. And oxygen. This is my draft copy. Let's see if I have any others like that. No, it's okay. Okay, so how many electron domains surround the oxygen? So there's 1, 2, 3, 4. Again, electron domains are either bonding. Those are an electron pair right there that's bonding. That's an electron pair that's bonding. This is a lone pair of electrons, and this is a lone pair. So 1, 2, 3, 4. So the answer is 4 to that. The steric number is 4. It's just another name for electron domains. The AXE for this is AX. There's 2 bonding, and there's 2 lone pairs. So AX2E2. Come over here to your chart. There it is, AX2E2. So the electron domain geometry is tetrahedral, and the actual molecular shape is it's bent. So this is going to be tetra and bent. And the angle is, because is less than 109, but because exactly it's water, it's actually 104.5. Water is very well known because it's such an important substance. Okay, there you go. What's the hybridization of the oxygen? Well, it's got 1, 2, 3, 4 domains. Again, it's part of the tetrahedral family, so it's Sp3. And what's the hybridization of hydrogen? None. No p orbital, you can't hybridize. Identify the sigma bond. So now we got to draw it. So here's the oxygen. And remember, it's still going to kind of form a tetrahedron. And it's going to have one sp3 orbital going up there. And that's going to have a lone pair. It's going to have another one coming up here somewhere. And that's an sp3 orbital. And that's going to have a lone pair on it. And then it's going to have these down here. And this one's bonded to a hydrogen. And then it's going to have another one down here, another bowling pin. All the SPs are shaped like bowling pins. And that's bonded to a hydrogen. So the sigma bonds are these two. There's the oxygen, there's the hydrogen, a straight line. SP, any kind of sp orbital, sp, sp2, sp3 are always sigma bonds. Okay, any time of just s orbital like hydrogen has is a sigma bond. We don't have any pi bonds because we don't have any double bonds. You don't see any double bonds up there, so there's no pi bonds. Okay, so the sigma bonds are this and this. All right, well, pi bonds, there are none. All right, let's keep rolling. Let's keep practicing these until they're just like you do them in your sleep. Okay, oxygen. This one's kind of interesting. Let's go ahead and do this. So D, how many electron domains? So we're just going to pick one of the oxygens because they're both symmetrical, identical. So how many electron domains? 1, 2, and 3 right there. So there's 3. That means the steric number is 3. And it is an AX. It has one bonding domain. Of those 3, only one of them is bonded. Doesn't matter whether it's single, double, or triple bond. It's one place where it bonds. So it's AX1, E2. 2 lone pairs. All right, what's the domain geometry? AX1, E2. Come on over here. And here's why this is not on your chart. This is a good one actually to do. This is not on your chart because it's only got 2 atoms in it. Your chart only deals with domains that have 3 or more atoms. So how do we deal with this then? Let's take a look at this. And what I want to actually do for this one is draw the energy level diagram for this. So what you have is you have 2s. And then you are going to hybridize. You need the hybridization of oxygen. I'm actually going to skip down to this one. You need an sp2. Why? Because you have 3 bonding domains. So even though you don't see an AX1E2, it is a trigonal planar. It's going to be a trigonal planar electron domain. But it is going to be linear because you can only form a straight line with 2 atoms. So I'm going to put that for the domain as trig planar. But what that tells us is molecular geometry is linear. So this isn't on your sheet because we're not used to dealing with 2. So here's what I'm going to write. I got a 2s. Let's do this down at the bottom. I want to show you this. So you got 2s and then you've got 2p. And that's going to be px, py, and pz. Now one thing we know is we see a double bond. That means we definitely are going to have a pi bond in here somewhere. Okay? So what we need to do is we need to, since it's going to be an sp2, we need to have this 2s right here and 2 of the p orbitals hybridized. So let me go ahead and just write that. So you've got sp2, sp2, and sp2. And then you've got a p, we'll just call it pz, which is an unhybridized orbital. Now what is the electron configuration when you draw it on an Aufbau, did an Aufbau structure? What does it look like for oxygen? Oxygen has 6 valence electrons. So it has 1 up and 1 down. It has 1 up there. It has 1 one down there, then it has one up there, and one up there. Okay, so it has two half-filled orbitals of the p's, and then one of the p's is entirely filled, and the 2s is entirely filled. So, how do we get this to be, what do we do with this to get it up to here? Well, you don't have to pass any electrons around. You simply have to move 2 electrons to here, 2 electrons to here, then you still have a single electron there, and a single electron there. So you have 2 suborbitals that can now bond. You can't bond if you have a full suborbital. They're paired up, they're married, they can't bond with anybody else. But these 2 can. So what that means is the other oxygen, which looks exactly like this, except it's flipped around in the other direction. So we no longer have this, we now just have this. The other oxygen is going to come in, it's going to put a down arrow there, and that is going to be an sp2 orbital. That's going to be your sigma bond right there. And then the pz, the unhybridized, is going to be the double bond. The reason this diagram is always kind of deceptive is this double bond, it looks like it's the same as the sigma bond. The pi bond here looks like the same. But as we just showed you, it's not. It really goes up like this and comes down. That's really where the pi bond is, up there, and the pi bond is down here. So it's up there and down here. It's not really in between. This makes it appear like it's a sigma bond, like it's in between the two, and it's not. So, in other words, this is this guy right here that paired up. That was the other oxygen coming in. And this pi bond is the other oxygen dropping an electron in there. And so that's the pi bond, and that forms the double bond there, okay? So the sigma bonds, I'm going to just, let's see how we do this then. Okay, so we have oxygen and oxygen, and you have sp2s. So let's just draw the easy ones first. There's an sp2. And there's a lone pair sitting out there. That's these guys. There's another sp2. And there's another lone pair out there. Okay, this guy has the same thing. So we'll go ahead and draw it for this. sp2 is going to have 3 lobes to it. And there's this lone pair out here. And then this one comes here, sp2. That lone pair. Now you comes for your sigma bond. So here is the lobe, and here's the sp2 here from this one. And here's the knob of the bowling pin, and here's the sp2 for this guy. So there's your sigma bond in between the 2 oxygens. And then you have that unhybridized p orbital. This guy right here is unhybridized, and we're just going to assume he's parallel to the page right here. And I'm just drawing him as a dashed line because he's not going to stay as a p orbital. He's going to become a pi bond. Again, a pi bond is a sideways bond. These 2 guys are sticking this way and this way, but they form a bond in this direction. They each have an electron somewhere in there. Let's just assume they're both up here, and they form a bond there. By the way, we haven't been talking much about the octet rule. So what happens here? You have a lone pair is 1, 2, 3, 4. Then this sp from the oxygen on the left has an electron. The one from the oxygen on the right has an electron, so they share those. So that's 6. 1, 2, 3, 4, 5, 6. And then the pi bonds each contribute an electron. That's 7 and 8. So that's the octet. That fulfills the octet rule. Okay? So again, anytime you see a double bond, you know you're going to have a pi bond. Anytime you see a triple bond, you're going to have 2 pi bonds. One that's parallel to the page, you can think of it like that, and one that's sticking out of the page, going away and in and out of the page. So the sigma bonds are simply, I'm going to draw an arrow to there, and the pi bond is this guy. And this is the same one. This is the same pi bond, just don't be fooled because it's in 2 different locations. Alright? Okay, so oxygen is a little more complicated than might have seemed, given that it's just a diatomic molecule. Okay. We are now to 15 and 16. Alright, we're almost done. So this assignment, once you get the hang of these, can go pretty quickly. I think the only thing I made it a little trickier for you is that you should start down here at D. So we got hydrogen cyanide, so HCN. So how many electron domains? There's 1 and there's 2. So the electron domain surrounding the carbon is 2, and the steric number is 2. Okay, what is the Axc notation? So it's A, X, there's 2 bonding areas, and no lone pairs around the carbon. I should say for HCN, I should have said for carbon specifically. But let's go ahead and we'll just leave that. Okay, so it's AX2E0. So now you can come over to your chart. There it is. It's a linear molecule. It's linear and linear because there's no lone pairs on the central atom. So up here we write linear and linear. Whoops, actually linear down there. Okay, the angle is 180 degrees. It's just a straight line. Okay, hybridization of carbon. So hybridization is AX2. You just come over here again. It's Sp. Now we haven't talked really about the hybridization of the outside, but if you look at the nitrogen, of course hydrogen cannot hybridize. We've talked about that in just about every problem. But this one has an electron domain there and an electron domain there, the nitrogen. So nitrogen also has an Sp hybridization. Doesn't have to be the central molecule, central atom, excuse me, to have hybridization. This can have hybridization too, and it does. Alright, so of nitrogen is Sp, so where are the sigma bonds? So let's go ahead and draw this. Here we go. Here's carbon, and we see it's Sp. The carbon is an Sp. That means it's got 2. An S and a P forms 2 bonds, so there's one. And here's the one that comes out this side. So let's take care of that hydrogen. It just has its little 1s orbital, and it bonds with the Sp of the carbon. Then this side Sp of the carbon bonds with, we said nitrogen also has an Sp, so I'll write an N there. And I'm going to draw my bowling pin for nitrogen there. So it's also Sp. And then the nitrogen's other Sp goes out the backside, and that just has those lone pairs on it. So these are all sigma bonds between the carbon and the hydrogen, between the carbon and the nitrogen, and well, you don't say the nitrogen lone pair is a sigma bond, but they're all on the internuclear axis, on the axis between two nuclei. Okay, now the fun part though. We see we have a triple bond, so that means you have to have 2 unhybridized p orbitals. So you've got one that's going up like this, one that's going down like that, and nitrogen has the same thing. And again, these form a p orbital like that on top and on bottom. So there's one of the p orbitals. That is a single orbital right there. So and then you have these 2 things coming out of the page directly at you like this, and they will form a p orbital up here, and again back down inside the page where I can't reach my pen, down underneath the table there, and that's going to form a p orbital back there. So you have 2 unhybridized p orbitals. Okay, so identify the sigma bonds. Those are the bonds right here between the hydrogen, the carbon and the hydrogen right there. It's also the bond between the carbon and the nitrogen right there. Those are sigma bonds. They're directly between atoms. The pi bonds, well, you've got 2 of them. You've got this one right here, which is also the same as this one right here. That's the same. And then you have the one coming out of the page that I can't draw, and going back into the page that I can't draw, and that's the second one. So just write down you have 2 pi bonds. Let me show you on the Aufbau energy levels how this would work. If we take the carbon, think about what carbon's electron structure looks like before it bonds with anything. It has a 2s orbital, and we know we fill that up with an up arrow and a down arrow, and then it has 4 p orbitals. And if you remember doing this, you put, Hund's rule says you put first electron there, then the second one there, and that's it for carbon. It has 4 valence electrons, 4 in its second orbital. 2 of them fill up the s orbital, and then you have one in the px, one in the py. The pz doesn't have one for carbon. So what happens when it hybridizes? What happens is this electron gets promoted up to the pz, and then because we need two bonds for carbon, we need one between the carbon and the nitrogen, one between the carbon and the hydrogen, it hybridizes to sp. So it hybridizes one s and one p. So it's going to look like this. It's going to look like sp, sp, and then up above is unhybridized py, we'll call it, and unhybridized pz, right there. And one of these electrons we said got promoted up there, so it now has an electron there, an electron there, an electron there, an electron there. Okay, so what happens here? The hydrogen comes along, this hydrogen comes along and puts an electron there, that's the hydrogen. The nitrogen comes along and contributes, right, that's what looks like an H. The nitrogen comes along and puts an electron right there. And then the nitrogen px orbital puts an electron right there. And the p, I said px, py, make it match up with this. And the pz puts an electron right there. So there's the double bonds right there. The double and the triple bond are right there. That's the sigma bond between the nitrogen and the carbon. That's the sigma bond. That's direct internuclear axis bond between the carbon and the hydrogen. So that's how that would look on an alpha orbital. Okay, we got one more to go with carbon dioxide. And so we've seen this molecule a lot of times before. It's got an interesting structure because the hybridization of the oxygens is different than the hybridization of the carbon. They can be different. Remember, outside atoms, terminal atoms, can have their own hybridization. You also have double bonds here, so it's got a lot of things going on. All right, so let's go ahead and start this. So how many electron domains surrounding the carbon atom? And the answer to that is there's 1, 2. So the steric number for carbon is 2. And the number of electron domains is 2. Now I want to answer the same question for oxygen. For oxygen, the number of electron domains is 1, 2, 3, and that's for each of the oxygen. So they're going to have 3 a steric number of 3 or 3 electron domains. All right, so this makes it a little interesting, different than some of the others we've done. What's the Axc notation for carbon and then for oxygen? So for carbon, the number is Ax2, and there's no lone pairs there, so it's E0. That's going to make it linear, and carbon dioxide is a linear molecule. Okay, for oxygen, it's going to be Ax1, E2. And again, that doesn't appear on our chart because our chart only deals with a minimum of 3 atoms in each of these. And if you look at the oxygen, it's only bonded to one other atom. So this is like the O2 example, the O2 problem that we did a little bit earlier. But what you would count is this: 1, 2, 3. There's 1 X and 2 E, so that's 1, 2, 3. So that would make it part of the trigonal planar domain geometry. Right here, it would be trigonal planar. What is the hybridization of carbon? Well, since it's Ax2E0, it's sp. What is the hybridization of oxygen? Since it's trigonal planar, it's going to be sp2. Put that down here. Okay, all right. Now we're going to draw this thing. And let's see, let's go ahead and finish answering the questions. So what's the domain geometry? Well, it's going to be linear. Since we're interested only in the central atom when we talk about domain geometry, it's linear, and the molecular geometry is linear. And the angle is 180 degrees. All right, so let's draw this. This is kind of an interesting situation. So we said the oxygen is sp2. That means it's going to have 3 orbitals coming off of it. And you need that because you have a bonding one right there with the carbon, and you have 2 lone pair. So I'm going to draw my sp2 orbital there coming off of oxygen. And there's the lone pair sitting out there. That's these two. And then you're going to draw another one coming down here. And that's the lone pair. That's those two. Let's do the same for the other oxygen before we go into the middle. So there's an oxygen, same thing. Okay, so we've taken care of the oxygen. Now oxygen has another bond going into the carbons. The carbon's in the middle here. And the carbon has just an sp. So here's an sp. And here's the oxygen with its sp2. It doesn't matter that one's an sp and one's an sp2. They still fit together and bond together. And here's the carbon with its other sp. Remember, there's two sps. And here's the oxygen with its third sp2. And there you go. All right, so now carbon has a double bond, and it has it in two directions. It has it this way and this way. So carbon has a p orbital. Let's just say it's the easy one to draw, which is the one going parallel to the page. So there's the p orbital for carbon that's parallel to the page. And oxygen also has an unhybridized p orbital. And this oxygen has an unhybridized p orbital. Like that. Okay, so what's going to happen is the second bond has to be a pi bond. So it has to be up here, and it's the same pi bond down here between the carbon and the left oxygen. And then it's going to have another pi bond over here between the carbon and the right oxygen. So you have, so again, this is one pi bond. It's that line right there. And this is one pi bond. These two together are one pi bond. It's that line right there. So let's look at where the electrons are here. Oxygen has to have an octet. There's 2 for oxygen. There's 2 more. That gets you up to 4. Then oxygen has 1 electron here, and the carbon has 1 electron here. They share those 2. That's what covalent means. They share the electrons. So there's 2 more for oxygen right there. And then oxygen has another one right here, and carbon has another one right here. So the oxygen shares these 2 in the pi bond. So oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons, if you count the shared electrons, which you do. Okay, so there's the double bond right there. Now if we go over to the other side, the oxygen has 1, 2, 3, 4, and then it has an electron out here in this sp2 orbital, and carbon has an electron in its sp orbital. So those 2 get shared. So there's 5 and 6 for oxygen. And now we'll draw the other 2 up here. One of them's up here, and that one's contributed by oxygen. This one's contributed by carbon. So now the oxygen has 1, 2, 3, 4, 5, 6, 7, 8, and that's the octet. And what about carbon? Carbon has 1, 2, 3, 4, 5, 6, 7, 8. So it also has an octet. Kind of a funny looking octet, but it works. Okay, so what are the sigma bonds? I'm not going to try to draw arrows. It's just anything that's on a straight line. This oxygen, these sp, any sps are sigma bonds. Okay, except the ones connecting to lone pairs. Okay, they're not. But between 2 atoms, sps are always sigma bonds, so those are sigma bonds. The pi bonds are the ones that don't lie directly between the 2 atoms. And those are the ones up here, down here, those right there. Those are the pi bonds, okay? So I won't draw those. All right, so that takes care of that. So it's a little bit challenging to learn this. It's a 3-dimensional subject, and we're trying to draw in 2 dimensions. Again, I would urge you to watch the video that I've put on the site for day 64. And I'm going to actually put that up for 65, 66, and 67. I want you to watch that video every night. It's only 12 minutes, and it's really, really good. And a lot of the diagrams I did here are based on the molecules that were in that diagram. But anyway, we'll see you in class. Hope you had a happy Thanksgiving, and we'll see you in class on Monday.